Hello, and welcome to another High Peak Education video. I would like now to discuss uniform circular motion and centripetal acceleration. Uniform circular motion is circular motion at a constant speed, and centripetal acceleration, which is directional acceleration. And this is all going to be two-dimensional motion in terms of kinematics and vectors. And for the calculus-based physics class, revisiting chapter 4, but from there, also going on quickly to chapter 6 to pick up both centripetal force and then non-uniform circular motion and non-uniform forces. Okay, so let's begin. Let's first define centripetal acceleration. Velocity has a vector which has both speed and direction. Acceleration is the change in velocity, which can be a change in speed in time, that is, speeding up or slowing down. But acceleration can also be a change in direction, directional acceleration. Now, up to this point in the semester, for a calculus-based physics 2 class, we focused almost exclusively on changing speed in time, speeding up or slowing down. That's because we've been focusing on linear motions, and we've been focusing on motion parallel to an axis, and the idea is that the accelerations have been speed accelerations. Directional acceleration is something we've basically neglected to this point. So that is a possible way to accelerate something. So notice this directional acceleration, this delta v, can be due to the velocity vector changing its direction only, but not its speed. So remember what Newton's first law says. A particle object continues to move in a straight line unless acted upon by an external or an outside force. So uniform circular motion, which is circular motion by definition, at a constant speed, means the particle directional acceleration is pointed toward the center of the circle. That is to say, if you take this velocity vector and this velocity vector and you subtract them, the directional vector subtraction points in toward the center of the circle. And we call this centripetal acceleration. So think of centripetal being like center trip or center seeking. So here's another way to show. Suppose a car is going around a circular roundabout, say clockwise here. Notice if this is v final vector and this is v initial vector. Suppose we show the vector triangle. Remember, v initial plus delta v should be v final. Another way to say this is v final plus the opposite of v initial. So we would put negative v initial over here would be delta v, which would be like so. And notice that that's not necessarily obvious, but the change in the velocity vector is indeed directed towards the center. Notice the change in position is from A to B, and the change in position vector is from A to B, that's a straight line, but the path is actually this blue dashed path. Okay, so we go in a circular path. Notice also the angle changes. We'll come back to that. That's delta theta. Okay, so it turns out, and I'm not going to go through the mathematical derivation, but the centripetal acceleration, which is going to be the magnitude of this change in velocity over change in time directionally, has magnitude v squared over r. So v is a constant velocity or constant speed. The speed squared divided by the radius will give the centripetal acceleration. Now AC vector is directed toward the center of the radius of curvature. So in the case of a circle, the center of the radius of curvature is, well, the center of the circle itself. Otherwise, it's the center of some imaginary sort of tangent circle to the path at the moment. And by the way, centripetal acceleration is many times also called radial acceleration. And radial acceleration is sometimes just defined with respect to some radial axis. Now, centripetal acceleration, notice, increases with increasing linear velocity or increasing speed. Okay. By the way, this linear velocity is sometimes also called the tangential velocity. I'll come back to that in later slides. Another way to say this is that if you're in your car and you're going faster, your speed is greater, it's harder to hold a turn. And that's because there's a requirement of a greater centripetal acceleration. Now, the centripetal acceleration increases with a smaller radius of curvature. So in other words, if this is a very small circle, as opposed to a very large radius circle, a sharp turn, small radius of curvature, is harder to hold that turn, because if r is smaller, AC required is bigger. Whereas a wide turn, where there's a much larger radius of curvature, requires a much smaller centripetal acceleration. And as a result, we don't need as large of a centripetal acceleration to give us, to hold us on the road, that is. Okay, so this should kind of make some sense about the magnitude of centripetal acceleration. Now, with this in mind, let's pictorially understand what we're saying. Notice that if an object's moving on a curve, imagine that there's this imaginary sort of circle that at the point that the object is on the curve barely touches the object, and this defines the local radius of curvature. As you might imagine, as turns change as you go along paths, the radius of curvature is getting bigger or smaller. Notice, in fact, here's some examples. Notice that as we go to a small radius circular racetrack, that's a small radius of curvature. Look at the green curve. This green curve is a larger radius of curvature, and blue is the largest radius of curvature there, with this being the center. Notice a straight line has infinite radius of curvature. That is to say, it's not curved at all. Okay? So we don't need any centripetal acceleration to hold us on this straight line. Here's another example where, say, a roller coaster is going through up and down turns, and you can see these sort of different radii of curvature. Now, here's an interesting thing. What if a car is taking a banked turn? Well, the car is going to have a certain angle that it's banked from horizontal. You might call that theta. But notice the radius is, again, imaginarily drawn from the center of this radius of curvature. By the way, that can sometimes be hard to define, but you estimate it as best you can from the geometry. But in many physics problems that you have to calculate with, that number is given to you. Okay, so I will perform a calculation, speaking of certain things, when I get to a later video. So stay tuned for that. In fact, I'll perform a couple examples here, as you'll see. What if we're in non-uniform circular motion? In other words, what if we're not moving around at a nice constant speed? What if, in fact, our rate of rotation is growing? Okay, well, that's a good question. So let's see what results. We can use centripetal acceleration to study the motion on curved paths where the speed changes. We should break the motion into the tangential and radial components. So imagine an object is moving along this orange path. Notice that the radial acceleration, which is essentially the centripetal acceleration, always points towards the center of the radius of curvature locally for that curved portion of the path. That's what we see in each of these locations. Whether that's a somewhat small circle or whether that's an extremely large circle, as we see right here. Okay? Notice, though, the tangential acceleration in general might vary wherever you are, because the tangential acceleration is the speed acceleration. That's what we studied earlier in the semester. That's speeding up or slowing down along the velocity vector direction that you're already pointing. So you can imagine when a car is hitting the gas or pushing on the brake and slowing down, those are both tangential accelerations because we're speeding up or slowing down in the direction that the object is already moving. Okay, so notice the total acceleration vector is the radial acceleration vector plus the tangential acceleration vector. So at any point of interest, the total acceleration vector is given by the sum of the acceleration tangent to the path and the acceleration perpendicular to the path. Notice that the tangential acceleration is always along and the radial acceleration is always normal, we might say, to the path. Notice when we add these two vectors together, depending upon their size, we can add them together using vector addition. And if we want to, we can actually also form a right triangle. That AR is one leg and AT is the other leg. And then A, the total acceleration vector, is the hypotenuse. Now the tangential acceleration, again, always going to change the speed of the particle. The magnitude of that acceleration should be dv vector dt. But this is v vector magnitude. So it's the change of speed with time. But the radial acceleration, which is the centripetal acceleration, that magnitude is v squared over r, so speed squared divided by radius. And the direction is given by what I've already said. The direction is either tangent to the path or perpendicular to the path. Okay, so I will show this example also in a later video. So thank you very much for your attention on this lecture. Please smash that like button if you like this content and it's valuable to you. Please subscribe to the channel to grow the channel. And I want to thank you for watching. Please share this with people within your sphere of influence to continue to grow the channel as well. So, for another High Peak Education video, thank you very much, and I will see you in the next video.